Hello, Algebra 2. I'm going to be going over the Unit 8 review. To begin with, to keep in mind, there are graphs on this review. Specifically, I give you an equation and an empty graph. You will not have to do that on my test. I repeat, there will not be any graphing on this test. The reason why is, well, if you have a graphing calculator, then you could just plug this in your calculator and see what it looks like. What I care about more is, can you recognize this as what it is? This is not a quadratic, it's not a linear equation, it's not an absolute value function, this is an exponential function. And the key component that makes it exponential is the fact that there is an x in the exponent spot, that our input is the exponent. That's the only thing that makes it exponential. So, rather than knowing what its graph looks like, because you can't always graph any equation in your calculator, I'd rather you recognize the form of this equation. All exponential equations are of the form y equals some constant a times some constant b, which is the base of an exponent x. So a, b to the x. And we need to recognize what the a represents in this equation and what the b represents in this equation. When we're looking at the a value, a represents the initial value. Another word for the initial value of a problem is the y-intercept of its graph. So how can we tell? Say we're looking and we know that a is the y-intercept. We know it's the initial value. How do I prove it? All y-intercepts happen at a coordinate where x is 0. Where we're starting at day 0, time 0, second 0. So we plug in 0 for the exponent, and we get 3 times 2 to the 0 power. But 2 to the 0 power is just 2 to the first, 1 power. It's 1, sorry. 2 to the 0 power is 1. Anything to the 0 power is 1. So 3 times 1 will just give us 3. We'll see what happens. When you plug in x is 0, out comes 3. So this is obviously an initial value. In fact, our a value will always be the initial. So if I look at all these functions, the a value is 3. So the initial value, the y-intercepts will be 1, 2, 3. The a value is 4. So the initial value will be 4. 1, 2, 3, 4. The a value here, hopefully you got it. This is of the form a times b to the x, and I know this 5 is b, not a, because it's the base. It's the base of the exponent x. It has nothing to do with a single constant a out front. There is a constant written out in front of this function, but it's not written usually. It's the number 1. This is 1 times 5 to the x. So, if there is no a value written, you assume it's 1. This initial value, its y-intercept is 1. Okay, so we have all the y-intercepts, all the initial values. What does b represent? If you recall, I gave a problem, a warm-up, where I talked about apples doubling every week. Well, this base to some power x, imagine this as the growth rule or the decay rule every week or every day. 2 to the first power, well, 2 to the 0 power, that's our initial value. When no time has passed, we start with 3. When 1 week has passed, what do we have? 3 times 2 to the first power is just 2. That's 3 times 2. We doubled. And then what happens when 2 weeks passed? 2 to the second power, that's 2 squared, that's 4. We doubled twice. So we're doubling and doubling every week, every day. This base, 2, is our factor. Either growth factor or decay factor. In this case, our factor is times 2, or doubling. So we know we start with 3, and then 1 day passes, or 1 week passes, at x equals 1. Well, now it's 2 to the first power, so we double once. 3 times 2 should give us 6. So somewhere up here. 1, 2, 3, 4, 5, 6. And then if we doubled 6, we would have 12. And if we doubled 12, we'd have 24. This graph grows very, very fast. Now, what happens when we go in the past? If in the future we times 2, times 2, times 2, when we go in the past to negative 1, well, that should be clear when we plug in a negative 1. Negative exponents flip the number. So 2 to the negative 1 will become 1/2, or 1 to the 2 to the first power. And 2 to the negative 2 would be 1 over 2 squared, or 1 to the fourth power. So we have going in the past is not times 2. It's the opposite, divide by 2. So if we started with 3, go 1 unit in the past, we should have half of 3, or 1.5. And go 1 unit in the past, we should have half of that. And then half and half and half. But notice, as we divide by 2 and divide by 2 and divide by 2, you can't keep dividing and ever get to 0. So there is an asymptote here at the value y equals 0, the x-axis. Because, well, divide, fold in half, you're never going to make something disappear and get to 0. So this is going to affect our domain and range. All exponentials have a horizontal asymptote. So our domain, well, we plugged in any amount of x's we want. We could plug in -1, -2, -3. We were allowed to plug in 0. We were allowed to plug in 1, 2, 3, 4. Our domain of all exponentials should be all real numbers. Infinity to negative infinity. So all of these are exponentials. All their domains are all real numbers. Their ranges, however, are all going to start at their asymptotes. So in all these functions, this rule right here, 1/10, every day or every week that we plug in for x, day 1, day 2, day 3, we're going to multiply by 1/10. So we're going to get smaller and smaller. This is a decay. A decay. Anything smaller than 1 would be called a decay. So rather than growing as we go towards the right, we should be falling and getting closer and closer to 0. So this asymptote should look something like this, where we approach 0 now as we go into the future. But we still start at an asymptote of 0, y equals 0. Same here, no difference. Start with 1, the initial value, grow by 5. So 1 times 5, times 5, times 5, times 5. We're growing by multiplying by 5. Our asymptote should be, again, at y equals 0. And this is going to affect our range. So we know the domains are all real numbers. Their ranges do not go down forever. They go up forever, so we do go up to positive infinity. So we are going greater. But we do start at the asymptote. And wherever the asymptote is where the range is. In this case, for all of these, it's at 0. And notice I put y is greater than, strictly greater than, no equal to, because you can't equal an asymptote. So in all these functions with the asymptotes at the x-axis, y is greater than 0. Okay, on problems 4, 5, 6, and 7, all it's asking is whether or not these exponential functions model growth or do they model decay. First, we got to notice that all of these are in the form a times b to the x. And the value that tells us whether or not it's growth or decay is the b value. A doesn't matter. A tells us where the graph starts, the y-intercept, and that's never super important on whether it's growth or decay. That could be the same for either. If it's growth, our b value is greater than 1. If it's decay, our b value is less than 1. And that should make sense. If I have a number greater than 1, like 2, 2 to the first power, 2 to the second power, 2 to the third power, it's times 2, times 2, times 2, it's growing. If it's less than 1, we're looking at decimals, or we're looking at, we're looking at fractions. So if imagine 1/2. If I take 1/2 and raise it to the first power, to the second power, to the third power, to the fourth power, I'm going to get something times 1/2, times 1/2, half of a half of a half. It's getting smaller and smaller. So we have, and our exponent could be negative, but that doesn't determine growth or decay. That usually determines which direction the graph is facing. So notice all of these graphs, they're going to the right, going to the right, going to the right, depending on growth or decay. But if you make the exponent negative, it's just going to flip-flop across the y-axis this time, so a reflection. So let's say we had this one. It's 1/10 decay. But then you made it negative 1/10. Negative 1/10 would just flip this graph across the y-axis, and we should have a function that is technically growing, but in the negative direction. So luckily you won't see anything like that on this test. For the most part, our b values will always be positive. So let's just go ahead and say greater than 0 while we're at it. B less than 1 and greater than 0, decay. B greater than 1, growth. So we have a 6. That's growth. We have a 9/10, that's less than 1, that's decay. We have 1.05, which is greater than 1 by 5%, so growth. And we have 5/4, greater than 1, so growth. Okay, on all of these problems, 8, 9, 10, 11, 12, 13, they have equal signs and then some of them have inequality symbols. But in all cases, if you have a base and an exponent on one side of the equal sign or inequality, and a base, and yes, this does have an exponent of 1, if you have more than one base on both sides, more than likely on this test, you're going to try to create the same base on both sides. That's almost always the goal you're trying to see. So I have a 3 as a base, and I have a 81. We're probably going to want to make the base of both sides of this equation 3. It's easier to turn 81 into a smaller base like 3 than it is to make 3 a bigger base like 81. So let's make both sides 3. This one's already 3, so 3 to the x minus 5. Can I write 81 as 3 to some power? Yes. 3 to the 4th power happens to be 81. So when the bases are exactly the same, we use this fact to say the exponents are also exactly the same, or at least follow the same pattern as the bases. So these bases were equal, these exponents are equal. And then we would solve it out. Add 5, that makes it 9. And then divide by 3, that would make this x equals 3. For 9, no work needs to be done. The bases are the same, just set the exponents equal to each other, which isn't that hard. And then we would solve it out. On number 10, notice we have an inequality this time. So I have a 3 and I have a 9. I want to change the 9 into the same base 3. 9 happens to be 3 squared. So this 9 is the value 3 squared. But originally, 9 was raised to the power of 4w minus 3. Well, so must this 3 halves. It's still raised to the power of 4w minus 3. When we do that, we combine this exponent 2 and the exponent 4w minus 3 by distribution, by multiplying. So we have 2 times 4w is 8w, 2 times negative 3 is negative 6, and we should have, on the right side of the inequality, 3 raised to the power of 8w minus 6 is greater than 3 to the 6w minus 5. So now the bases are the same, but we have an inequality. In this case, the inequality maintains. 3 is less than the base 3, therefore this exponent is less than this exponent. So we should solve 6w minus 5 is less than 8w minus 6. Solve it all out and we'll get an answer. You can check your answer key for that. Okay, next we got something like number 11. The rest are pretty much the same, solving 8, 9, 10, 12, and 13. But I just wanted to touch on what do you do when your base is a fraction? So I have a 2, and I have a 1 over 8. I know 2 and 8 have something to do together. I know 8 can be written as 2/3. But right now that would be 1 over 2/3, and that's not okay. So how do we flip a fraction? Just make sure its exponent is negative. So 1 over 2/3 is the exact same thing as 2 to the negative third power. So 1 over 8, if we want to flip it, would just become 8 to the negative 1. And then 8 is 2 to the third power. So just wanted to touch on that. So we have 1 over 8. We could write that as 2 to the negative third power instead of 2 to the positive third power. And 2 to the 3n minus 1 is greater than or equal to 2 to the negative 3, and it's originally raised to the power of n. Negative 3 times n is just negative 3n. So we have 3n minus 1 is greater than or equal to negative 3n. I guess add 3n to both sides, we get 6n. Add this 1 to the other side, we have greater than or equal to 1. Divide both sides by 6, and we have n is greater than or equal to 1/6. Okay, when we're writing things from exponential form into logarithmic form, there's 2 ways we could go about it. One is translating. If you understand what parts this exponential function is, b is the base, n is the power, and x is the answer to this exponent, then you should know where each part goes. Log base, and we say log base because the base of the log matches the base of the exponent, of, well, when we say of something, we're always taking of the answer, which is why we replace it, answer becomes the argument, log base b of x. And if you don't remember the x goes in this spot, we're not taking the log of x, just remember what should be opposite of a log. Logs always equal an exponent. And the exponent of that exponential equation is n. So no matter what, the n has to go opposite of the log. So translating, the base is b, the exponent is n, so that goes here, and the answer to the exponential becomes the argument. I would say translating is fine if you're working really fast, but if you're ever working with an inequality, or if you forget where each part goes, use the cancellation properties. So take b to the n equals x. Now, exponents and logs are inverses of each other. They undo each other. So if I want the base b to disappear, and I just want to be left with an n, log both sides. So I'm going to take log of b to the n, and what base should I have? A base that matches the base I'm already given. Log base b of b will cancel, and I'm left with n on one side. And if I do it to one side, I should do it to the other. So take this x, log it, log base b, both sides. Log base b of x can't be resolved, but I have the other side of the equation, log base b of x. That is going from exponential to logarithmic form. But notice the only difference between translating and canceling is I naturally, personally, put my logs on the left, and when I cancel, the logs end up on the right. When you cancel, it'll help you out with the inequalities, because let's say this wasn't equal to. Let's say it was just less than. Then no matter what, all the way down through this problem, it's less than. N should be less than the log. Whereas if we're translating, if this started as less than, then it would end up as greater than. And I don't like doing that conundrum of deciding which direction the inequality should face. I'd rather just cancel all the time, or cancel in my head. So an example of that, I have 9 is the base, 0 is the exponent, 1 is the answer, or the argument. So if I want to get rid of the base 9, I log it. Log base 9 of 9 to the 0 equals, do it to both sides, log base 9 of this side 1. We're left with, log base 9 and 9 cancel, we're left with a 0, equals log base 9 of 1. And then just by canceling, you've converted exponential into logarithmic form. So, maybe one more time with 6 cubed equals 216. I want to get rid of log base, or I want to get rid of base 6, so I log it to base 6. That cancels out the 6, I'm left with 3. I do it to one side, I do it to the other, so I'm left with log base 6 of 216 is its logarithmic form. Okay, going from exponential to log is the exact opposite. Notice when we wanted to get rid of an exponent, 4 to the 5th, we log it to the correct base. If we want to get rid of a log, we make it the exponent of the correct base. So when I write 2 and I'm writing it lower than this log base 2 of 8, I'm taking this whole side of the equation and I'm doing something called exponentiating it. Exponentiating. So what does it mean to exponentiate this side of the equation? Turn this whole side of the equation into an exponent. The exponent of what base? The same base that we're trying to cancel. So 2 raised to the power of log base 2 of 8 will have a cancellation, and we're left with 8. Do it to one side, do it to the other. So take the whole right side of the equation, the value 3, and make it the exponent of the same base 2. So 8 equals 2 cubed. And that is a true statement. So we've converted it to its exponential form. So one more time. If we take, let's say, log base, here's a good example. 19 and 21 are the same base log. See how this is log base 10? If there is a log given and there is no base written, you assume it's 10. That is the common log. So if I just give you log of x assume that is the same thing as log base 10 of x. Log base 10 if there is no logarithm. So I want to get rid of the base 10. I take this whole side of the equation and make it the exponent of 10. Take the whole right side of the equation and make it the exponent of 10. 10 and log base 10 cancel. I'm left with 100 equals 10 squared. And that is indeed a true statement. Take 36, log base 36, get rid of it by making the power of 36. Make this side the power of 36. I'm left with 6 equals 36 raised to this side of the equation. 36 raised to the power of 1/2. Or that's the square root of 36. Square root of 36 is definitely 6. This works. Cool. And if we're evaluating the expression, it means evaluate because there is nothing on the other side of this equation side. There's no equal sign. What they want you to do is find out, what does this log base 3 of 81, what's it equivalent to when simplified? And all of these can be answered. But recall, all logs, answers, are exponents. So every single one of these logs equals an exponent. If you're unsure of how to start, you could always cancel the logs by making it a power of 3. If you do it that way, we actually need a value here. So you could translate this into log base 3 of 81 equals some unknown and name your unknown. You could name it x, y, whatever. You could even name it question mark if you want. Let's just say x. If you were going to cancel the logs, you have to have a variable on this side, and now we have 81 equals 3 to the x. And it becomes super clear what this question is asking for. X is the exponent. Well, what's the exponent that relates 81 and 3? It's 4. 3 to the 4th power is 81, so the answer to this question is 4, because 3 to the 4th power is 81. Sorry, I read that here. 3 to the 4th power is 81. Or you just read the question and say, what's the exponent that relates 2 and 1/16? Well, if I want it to be 16, 2 to the 4th power is 16. But I want it to be 1 over 16, so make it negative. 2 to the negative 4th power. That would flip the equation, because it's negative, and make this 1 over 2 to the 4th. And 2 to the 4th happens to be 16. So 2 to the negative 4th is the answer to this question. It's the exponent that makes this true. Or sorry, not 2, just the negative 4. So 3 to the 1/3. It's the same number. Base became the same number. I just need to flip it. So the answer, the exponent that makes this true, is negative 1. 3 to the negative 1 makes 1/3. So the answer is negative 1. The most important part about this section, 26 through 33, is this statement in the directions that says check your solutions, which means there are times when these solutions could break, or we could have no solutions, or we could lose a solution. What are we checking when we're looking at logs? If you recall, the definition of a log requires our base be greater than 1. You never really have to worry about base greater than 1. So log base 5, log base 2, log base 2, log base 9, all of these bases are greater than 1. In my class, you should be given a base greater than 1, except maybe on number 29, and we'll take a look at that. But the arguments are what we really need to check. An argument must be greater than 0. So if I look at log base 5 of x greater than 3, the argument is x. And since the argument is x, that whole argument has to be set greater than 0. That's the only thing we got to check. Okay, cool. Nothing to solve there. X just has to be greater than 0. We translate this to its exponential form. Log base 5 of x is greater than the exponent 3. In other words, if we translate this, recall I said translating will give us the conundrum if we're not sure of which direction the inequality face. So let's say you say the base is 5, the exponent is 3. Which direction should this thing be on? To the left of the inequality or to the right of the inequality? Rather than guess, just cancel the log and say, get rid of log base 5 with the base 5. And do it to one side, do it to the other. We have log base 5 and 5 cancel. X is greater than 5 cubed. And I know for a fact this inequality is facing this direction. Easiest way to do it, cancel the logs. So I'll say here, cancel logs, don't translate. Cool. So we have x is greater than 5 cubed is 125. And then we look at this argument that we got. Does our answer satisfy the argument? X is greater than 125. Well, every number I can think of greater than 125 is already greater than 0. So we don't need to tack on that inequality. Whereas, if I look at something like log base 4 of m is less than 0, make both sides the exponent of 4. These cancel. I'm left with m is less than 4 to the power of 0, which is m is less than 1. And then we look at the argument, m. The argument must always be set greater than 0. And then we think, does our answer always satisfy the argument? Numbers less than 1 are always greater than 0? No. -2 is less than 1, but it's not greater than 0. So this implies that we have to tack on an extra answer, that m is not only greater than 1, less than 1. It has to be less than 1 and also greater than 0. And if you don't write this as the full answer, you would be wrong. So m less than 1 is an incomplete answer. It would not be good enough. Whereas writing it fully as m is between 0 and 1, perfect. Okay, when you're solving a log and its base is the unknown, log base x, and we're solving for it, recall that the base needs to be greater than 1. So we just need to know whatever this x value is, whatever this base is, at all times it must be greater than 1. And then we solve it like usual. Get rid of log base x by making it the exponent of x. Make this side the exponent of x. We're left with 16 equals x to the 4th power. Now what number should go here? What base raised to the 4th power equals 16? 2. 16 can be written as 2 to the 4th power. So x must be 2. And then we go back and think, are there other numbers that could fulfill this this base? Well, -2 to the 4th power, -2 times -2 times -2 times -2 is also positive 16. So this could theoretically be plus or minus 2. But then we take that and look at the fact that the base has to be greater than 1. If it was -2, it would not be greater than 1. So we're only going to take the positive version. Positive only. Because x has to be greater than 1. Okay, 30 and 31 are probably the longest problems on this review packet. I recommend doing these on a separate sheet of paper. 30 is as easy as the ones you've seen on the quiz you've taken, and definitely practice 30. 31, on the other hand, if you've looked at my answer key, is absurdly long and very complicated because we're taking the log of x squared minus 1, and it's an inequality of a quadratic. That makes this harder than it should be. So if you want something to practice, try 31. If you are just trying to get by on this test, I say you could skip this problem. But let's look at 30. Log base 2 of 5x plus 10 is less than log base 2 of 3x minus 12. The bases are the same on both sides. That makes me think these are going to cancel. How do I prove it? Log base 2, get rid of it by making the exponent of 2. Do it to one side, do it to the other, and yes, both sides indeed cancel, and we're left with the arguments 5x plus 10 is less than 3x minus 12. We solve this out. Let's see. Minus the 3x to the other side should give us 2x. Minus the 10 to the other side, and we should get negative 22. Divide both sides by 2. X is less than negative 11. Okay, we got one answer. And then we look at the arguments. You must always check your solutions. And we check the solutions by checking the arguments are greater than 0. So let's look at 5x plus 10 and 3x minus 12. In 5x plus 10, we have 5x plus 10 greater than 0. If 5x plus 10 is greater than 0, subtract 10 to the other side. We should have 5x is greater than negative 10. Divide both sides by 5. X is greater than negative 2. Okay, keep this answer in mind. On the other argument, 3x minus 12, let's set it greater than 0. 3x minus 12 is greater than 0. Add the 12 to the other side, divide both sides by 3, and we have x is greater than 4. Let's look at this inequality. For this log to be possible, all three inequalities have to be true at the same time. Now, which inequalities we write as our answer depends on which inequality is stronger than the others. I'll explain what that means. First, we need to be less than negative 11. So think of numbers less than negative 11, like negative 12 or negative 13. If I'm less than negative 11, am I greater than negative 2? Let me look at a number line to show what I mean. If I am less than negative 11, am I greater than negative 2? The answer is no. There's no way that you could be both less than negative 11 and greater than negative 2. So this flat out is impossible. There is no number less than negative 11, which is only negative numbers, that would make either of these arguments true. 5 times a negative number less than negative 11, like negative 12. That would definitely not stay greater than 0. So this is not possible. This has no solution. Or the no solution symbol. Okay, solving logarithmic equations. Again, the bases are the same. This whole test is same base. So if the bases are the same, you might as well cancel them, and we're left with the arguments. K squared minus 2k equals 24 plus 3k. Now this is a quadratic equation, which means we must solve this by getting everything to one side and setting it equal to 0. I'm going to leave my k squared on the left so it stays positive. So let's minus this 24 and minus this 3k to the other side. Let's see, negative 2k minus 3k would give us negative 5k, minus 24, and k squared out front. All of this equals 0. We're looking for, well, first, a is equal to 1. Our leading coefficient is equal to 1. So I can just write k and k. We're going to factor this. And then we're looking for two numbers that multiply to AC and B, add to B. So AC would be 1 times negative 24. And B would be negative 5. We want to multiply negative 24, so 8 and 3, which one's negative? Adds to negative 5, so make the 8 negative and the 3 positive. So negative 8, positive 3, all this equals 0. Set this equal to 0. K minus 8 equals 0. K must equal positive 8. K plus 3 equals 0. K must equal negative 3. Now we check these answers before we finish. Because remember, these arguments, k squared minus 2k and 24 plus 3k, must be greater than 0. So let's see. Plug in 8. 8 squared is 64. Minus 2 times 8, 16. 64 minus 16 will definitely stay greater than 0. So this side works. 24 plus 3 times 8. Well, 3 times 8 is 24, so this is 24 plus 24. And that's greater than 0. So 8 is A-OK. Negative 3, let's see. Negative 3 squared is positive 9. Minus 2 times negative 3. Negative times negative is positive, so this is positive 9 plus 6, greater than 0. So this side works. Negative 3 here is 24 plus 3 times negative 3. This is going to end up being 24 minus 9, but that's still greater than 0. So both of these answers work. Next one over. The bases are the same, log base 9, log base 9. We're left with negative 2r equals negative 4r plus 4. Let's say add the 4r to the other side. 4r minus 2r is 2r equals 4. Divide both sides by 2, r equals 2. Check this number. We have two arguments here, negative 2r and negative 4r plus 4. If I plug in 2, negative 2 times 2 is not greater than 0. This is broken. How about this side? Negative 4 times 2 would be negative 8. Negative 8 plus 4 is also not greater than 0, so this side is broken. This problem cannot have r equals 2 as an answer. This problem has no solution. Okay, once again, we've got some logarithmic graphing problems. Remember, there is no graphing on this test. Instead, I need you to understand the domain and range of any logarithmic function. So, if you look at these, this is 2 and an x minus 1. These are just the usual transformations. 2 is a vertical stretch, and x minus 1 is right 1. Those aren't that interesting once you know what the parent function looks like. But there's infinitely many exponential functions and infinitely many log functions because these bases, 6, 2, and 3, can spawn any amount of parent functions as we want. So let's look at 35, log base 2. The parent function of this transformation was this right 2 down 1 is log base 2 of x. So let's look at that. Y equals log base 2 of x. And let's look at its inverse, its exponential version, which is y equals the base 2 raised to the power of x. These are exact opposites of each other, inverses of each other. Now, what does it mean for something to be an inverse? We take every x and every y of both functions and flip them in order to get the other. Now, what does that look like? Y equals 2 to the x. If we imagine that function, let's put a nice graph here real fast. Let's say that's good enough. Let me shrink this down to size. Cool. Let's say we take a look at this function. All right, y equals 2 to the x. Well, where should we begin? X and y. We know we could plug some values in for x. The usual ones are -1, 0, and 1. Maybe 2, but -1, 0, 1 is good enough for now. 2 to the negative first power would be 1/2. It's flipping the base. 2 to the 0 power, anything to the 0 power is 1. And 2 to the first power is 2. So what have I been given here? The initial value, which hopefully you can notice, a times b to the x. There is no a written, so we assume it's 1. This initial value was always going to be 1. So 0, 1, -1, half, and 1, 2. And imagine if we keep going further and further in this direction, we'd get closer and closer to the x-axis, but never quite. There is an asymptote at the x-axis because our y value will never equal 0. So this is our 2 to the x. Something like that. And then we look at log base 2 of x. Log base 2 of x is a little hard to graph in a table unless you take a look at maybe its exponential translation. So the base is 2, the exponent is y, and the answer is x. So 2 to the y equals x is the same thing as log base 2 of x. And notice, compared to the exponential function, we've indeed shifted the x and the y and flip-flopped them. So now our y values are the exponent. Let's plug in y values. That'll make our life easier than plugging in x values. So let's say a y, let's make it -1, a y, make it 0, and a y, make it +1. Then what are the x values that would come out of this? 2 to the -1 is still 1/2. 2 to the 0 power is still 1, and 2 to the first power is still 2. But notice where I'm going to plot these. 1/2 -1 would put us here. X is 1/2, y is -1. 1, 0 is now an x-intercept rather than a y-intercept. And 2, 1 would place us here. And now, if you notice, we have a new asymptote along the y-axis for the logarithmic function, where we get closer and closer to the y-axis, but not quite. This is definitely the graphs of two inverses of each other because they are reflections across the line y equals x. All right, so what's important about this is the domain and range. You could graph every single one of these functions in your calculator, but I do want you to recognize their asymptotes and domain and range of a log. So the asymptote of the exponential function, the asymptote, was the x-axis, or y equals 0. The asymptote of the logarithmic function is the y-axis, or x equals 0. So the x and the y flipped. Now, the domain of any exponential function is all real numbers. The range is y is greater than whatever the asymptote is, in this case 0. Flip-flop that for the domain of the logarithmic function. The domain of any logarithmic function is x is greater than whatever its asymptote is, in this case 0. And its range will be all real numbers. So notice the range and the domain flipped for the log and exponential function. The domain and the range flipped for the log and the exponential function. And now we could at least see some basics of what these graphs might have to do. But I know the domains of all of these. If they've shifted right, then all of their asymptotes have shifted right. So in this case, this one went right 1. Its domain is all the x values greater than 1, the asymptote. This one shifted right 2, so all of its domain values are all the values greater than 2. Its asymptote is at x equals 2. This one shifted right 2, so its domain is also greater than 2. Its asymptote is at right 2. For the ranges, doesn't matter if we shift up or down, the range of any log function is all real numbers. And that's good enough, because you could graph these pictures in your calculators. But all I really need you to see is the domains change with the asymptotes, and the ranges of a log function will be all real numbers. Flip-flop that with exponentials. The domain of all exponentials is all real numbers. And the asymptotes will be the range. Y is greater, well, this graph didn't shift up or down at all, so y is greater than 0. This graph did not shift up or down at all, so y is greater than 0. Same with this one, y is greater than 0. These asymptotes all happen to be in the same place. These log asymptotes just shifted because we went right 1, right 2, right 2. Okay, last section, we've got word problems that'll be on the test. I highly recommend do not take this test until you've looked through these word problems. On my test, I'm going to give you the equation you're supposed to use on every word problem you see, but if you don't know what's supposed to go in the A spot or the R spot or the T spot, you're kind of sunk. So, follow along. In 1985, there were 1,200 eagles. They reproduced at a steady annual rate of 0.07. What will the population be in 2008? And they tell me to use this equation. Well, if I'm given y equals a times 1 plus r to the t, this is the form of an exponential function. A times b to the x. A is still the initial value. So we have whatever the initial value of this problem is a. But rather than a b, like doubling is 2, tripling is 3, we have 1, which represents 100% of the original. And we have r, which represents the increase of that 100%. So this is the rate. T should be obvious. T is just time. Okay, using all these facts, this is a 1 plus r because these eagles are growing. They're reproducing. So the initial value should be 1,200 eagles. Why? Because it's the first year they gave us. Now, the one thing I want you to keep in mind, we just called A 1,200. If we did, then 1,200 is a y-intercept. It's an initial value. So don't think of this as a coordinate 1985, 1,200. Think of it as the coordinate 0, 1,200. The year 1985 is year 0, which would make the year 2008 year 85 to 2000 would be 15 years, plus 8 would be 23 years. So the point we're looking for is what happens 23 years later. Do not plug in these full years, 1985 and 2008. Otherwise, your graphs are going to look massive from 1985 all the way to 2008. Instead, just use 0 to 23. It'll make your life a lot easier. So 1200 is the initial value. 100% is still there. The rate, they've given us 0.07. The question is, can we plug in 0.07 or do we have to convert it? The answer is we can plug in 0.07. The reason why is the only time we have to convert is if they gave me this as its percentage form, which they didn't. 0.07 just happens to be 7%. We cannot plug in 7%, but we can plug in 0.07. Okay. All of this is raised to the power of t, which is time. That happens to be 1985 to 2008 is 23 years. From here, we're just solving for y, what this is going to equal out to. So y equals, let's clean this up a little, 1200 times 1.07 raised to the power of 23. I'm going to pause for a second and give the answer. Okay, from here, it's as easy as plugging into the calculator. So let me pop up my calculator. And we're going to graph, what was that, 1200 out front, parentheses, 1.07, raised to the power of 23. 23 years. And we get our answer, 5,688.64. And that's good enough. Well, though we should probably round this to whatever answer we get. So 5,688, and it says rounded to the nearest whole number. 0.64 would round us to 5,689. So eagles. Okay, number 38 is solved largely the same as 37, so let's skip to 39. The key word here is compound interest, and this formula will be given to you on the test. Compound interest is total amount equals principal times 1 plus r divided by n raised to the time times n. So we got total amount. This is the amount of money you make at the end. Principal, if you notice where it's placed in the equation, it's where the a usually is, principal. And it's our initial value still. 1 plus r of n, r is still the annual rate, but we're dividing that rate up into several n's, which we call periods. T is still time, or usually years, and n is the periods. So the amount of years that pass, we are multiplying every year times the amount of periods. So the key thing here, probably that you may or may not remember or have seen before, is what is a period? So imagine I give you a certain amount of rate for the interest rate. In our case, 3%. This is our R. But I'm going to compound more than once a year. So maybe not annually. Annually is just once a year. So this word here lets us know the number of periods. Annually is 1. But that's not really compound interest because once a year is just normal interest. This could be other terms like quarterly, which is 4 times a year, or monthly, which would make our period 12 times a year. Let's choose monthly, just for the sake of actually having compound interest. So instead of annually, let's choose monthly. So let's say we have a full interest for a year, but we're compounding it monthly. That means 12 times a year, you're taking this 3% interest and dividing it by 12. So a small percent, very, very small, whatever 3 over 12 is. But it's happening 12 times, and that's enough to make this increase much faster. So the percentage is less important than how many times it happens. So take a smaller percentage, like 3 over 12, but make it happen more times, we're going to have a bigger amount of money at the end. So Sam opened a savings account of compound interest of a rate 3%. So we know our R, 3%. Let P be the initial amount. Well, thank goodness they told us. Principal is the initial amount. Sam deposited, and let T be the number of years the account is open. Find an equation to find A. So the total amount after T years. Assume that Sam made no more additional deposits or withdrawals. So principal, let's see, are they going to give us a principal? If Sam opened the account with $500, there's our principal, initial amount, plus times 1, which is 100%, plus the interest rate, 0.03, 3%. And we said monthly, not annually. So we're dividing this into 12 chunks, 12 months. And how many years are passing? We have 10 years later. So 10 years times the number of periods. 12 months happens 12 times a year. So 12 times every year would be 12 times 10. Take this whole thing and plug this into your calculator, and you'll find an answer. Okay, last set of problems we'll be looking at is write an exponential equation given 2 points. First, we need to know what an exponential equation looks like. They're all of the form y equals a times b to the x. And we need to find out what is a and what is b. A, we should always check if a was given to us. Recall, a is an initial value. So 0, 2 is actually a because it's an initial value. It's a y-intercept. So I know this equation right off the bat can be written as y equals 2, which is our value of a, times b to the x. To solve for b, we just need to plug in x and y, and they've given us an x and a y. So -3 will go in the x spot, -4 will go in the y spot, and we have -4 equals 2 times b raised to the power of -3. And then we just solve. Divide both sides by 2. We've got -2 equals b to the -3. We want to get rid of the -3rd power. There's a couple of ways you could think about it. Negative exponents flip, so this could be considered 1 over b cubed. And then we could cube root it to get rid of the cube. Or, all at once, we could get rid of the -3 by raising it to the power of -1/3. Do it to one side, do it to the other. Negative times negative is why I made it -1/3. This is going to become positive. 3 times 1/3 is 1, so we're left with b to the first power, or just b. -2 raised to the power of -1/3. Negative exponents flip, so this is going to become 1 over -2 raised to the positive 1/3. And the positive 1/3 power is just the cube root. So b is 1 over the cube root of -2. And I can't do the cube root of -2. Not because it's negative. The negative's a-okay. This is not an imaginary number because that is an odd root. But I don't know what the cube root of 2 is, or I don't want to write it as an irrational decimal. So I'm just going to leave it as 1 over the cube root of -2. We take our two values, a and b, and we finish it off by writing our equation. Y equals 2 times 1 over the cube root of -2, all of this raised to the power of x. And we have our exponential equation.